Hi, this is Dr. Bay, and here's Bugsy, and today we're going to go over the SN1 mechanism. We'll delve into reaction kinetics, arrow pushing, transition states, and stereochemistry, so stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy, soaring through the sky, triumphantly we fly, give rise to the complexity of life, living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
A nucleophilic substitution is a type of reaction in which one nucleophile replaces a leaving group at a tetravalent sp3 hybridized carbon atom. There are two mechanisms for nucleophilic substitutions that you're going to learn about in this course. The difference between the two mechanisms lies in the timing of the bond breaking and bond forming steps. The mechanism that we're going to go over today is called SN1. Now, if we break this down, the S stands for substitution, N stands for nucleophilic, and 1 because the reaction is unimolecular and only one species or molecule is involved in the rate determining step, which we'll get into details in a bit. For now, let's go over the basics of the SN1 mechanism, which is a two-step mechanism. In this example, 2-chloro-2-methylpropane reacts with methanol to form 2-methoxy-2-methylpropane and hydrochloric acid. The first step of the SN1 reaction is that the leaving group leaves and a carbocation intermediate is formed. This first step is slow and is the rate determining step. Now, the second step of SN1 has two parts. In step 2A, the carbocation reacts with methanol to form an oxonium ion. Recall that the carbocation is our electrophile and methanol is a weak nucleophile because it's overall neutral. And then in step 2B, a proton transfer occurs. Cl- deprotonates the hydrogen, and then the bond between O and H becomes a new lone pair of electrons in the final product. We can plot the reactants, intermediate, and products of an SN1 mechanism on a reaction coordinate diagram that essentially displays how much energy a reaction requires in order to form the products. The x-axis shows reaction progress, while the y-axis shows energy. On the left, we start the curve at our reactants, which would be our starting substrate, the alkyl halide. From here, it takes a certain amount of energy called activation energy to reach the transition state. Activation energy can also be written as E sub A. Then, from the first TS, the reaction goes to form the carbocation intermediate. And then the nucleophile attacks as the reaction goes back up to TS2 and then goes back down to form the new product. The amount of energy between reactants and products is the Gibbs free energy delta G or enthalpy delta H, depending on what type of energy values you're analyzing. An SN1 reaction occurs fastest and is most reactive when the electrophile is tertiary. The SN1 reactivity decreases as you go from tertiary alkyl halide to a primary alkyl halide. And an SN1 reaction is completely unreactive with methyl halides. Notice that this trend is completely opposite to that of an SN2 reaction. Here is a table of various nucleophiles. SN1 reactions work best with weak or poor nucleophiles shown in red on the right side of the table. All of these nucleophiles are considered to be neutral. On the other hand, SN2 reactions work best with strong or good nucleophiles shown in green on the left side of the table. However, if the reaction uses a moderate nucleophile in the center of this chart, you have to consider other factors of the reaction, such as solvent and type of electrophile, to help differentiate between the mechanism being either SN1 or SN2. Here's a table of common solvents that you may come across. SN1 reactions prefer polar protic solvents shown in green on the left, while SN2 reactions prefer polar aprotic solvents shown in blue on the right. And the rate of an SN1 reaction only depends on the concentration of the electrophile, making this reaction first order. And SN1 reactions work best, again, with tertiary alkyl halides, weak nucleophiles, and polar protic solvents. If an SN1 reaction occurs at a chiral center, you will form products that are racemic mixtures, which is when both the R and S enantiomers are formed in equal amounts. In this example, you start with the R enantiomer, and then the leaving group, bromine, first leaves to form a carbocation intermediate. Recall that the geometry of a carbon with 3 bonds is considered to be trigonal planar. So because this carbocation intermediate is flat, the nucleophile can attack from both faces of the carbocation. And because there's no preference as to which face it would attack from, you produce both products, the R and the S, in equal amounts, known as a racemic mixture. So, to compare SN2 to SN1, here's a chart comparing the types of electrophiles, or alkyl halides. If you had a methyl alkyl halide, SN2 is favored and SN1 will not occur. If you had a primary alkyl halide, SN2 is favored and SN1 rarely occurs. If you had a secondary alkyl halide, SN2 will occur if you had a polar aprotic solvent with a good nucleophile. However, if you had a polar protic solvent with a poor nucleophile, then SN1 would occur with a secondary alkyl halide. If you had a tertiary alkyl halide, SN1 is favored. And lastly, if your alkyl halide was at a stereocenter, the SN2 mechanism would invert the stereochemistry of the products, while the SN1 mechanism would form a racemic mixture of products. Now let's do some examples if you had a secondary alkyl halide. So in the top example, you have to identify which type of nucleophile you have and what type of solvent. Here, NaOH can be rewritten as Na plus and OH minus. Since OH minus has a clear negative charge, that means it's a strong or good nucleophile. And DMF, or dimethyl formamide, is a polar aprotic solvent. So with those two factors in mind, this means that this will be an SN2 reaction. And since the electrophile also has a chiral center, the SN2 product should have an inversion of stereochemistry. In the second example, we're using the same secondary alkyl halide, but now it's reacting with water. H2O is a weak or poor nucleophile, and it's also a polar protic solvent. This means that this particular reaction will be SN1. And since the electrophile has a chiral center, remember that SN1 is a two-step reaction where the leaving group first leaves, and then a carbocation intermediate is formed. Remember, since carbocations are planar, water can attack from both faces, making the final SN1 products a racemic mixture. So to summarize, SN1 is a two-step mechanism where the leaving group leaves to form a carbocation intermediate, then a weak nucleophile attacks the carbocation, and then a proton transfer occurs to form the final product. SN1 reactions prefer tertiary alkyl halides, weak nucleophiles, and polar protic solvents. And the rate of an SN1 reaction only depends on the concentrations of the electrophile. And lastly, if substitution at a stereocenter is occurring, a racemic mixture of products forms.
Organic.